Right now, as you read these words, our Milky Way galaxy is in the middle of a cosmic feeding frenzy that has been ongoing for billions of years and shows no signs of stopping. Like a massive cosmic predator, our galaxy is actively tearing apart and devouring smaller neighboring galaxies in a process so violent and spectacular that it is reshaping the entire structure of our cosmic neighborhood. We thought galactic cannibalism was a rare, ancient phenomenon that occurred during the universe's chaotic early epochs, but we've discovered that our own galaxy is a serial killer that continues consuming its victims in real time. Here is what makes this discovery so profoundly disturbing. The Milky Way isn't just passively growing through occasional mergers. It is systematically hunting down and dismantling dozens of smaller galaxies, simultaneously through gravitational forces so powerful they can stretch stellar systems across millions of light years while scattering their stars throughout our galactic halo like cosmic breadcrumbs marking the scenes of galactic murders. The evidence is written across the night sky in stellar streams, rivers of stars torn from their home galaxies and stretched into impossibly long filaments that wrap around our galaxy like ghostly ribbons marking the death throes of cosmic communities that once contained billions of stars, planetary systems, and potentially entire civilizations. The Sagittarius stream alone spans more than 360 degrees around the sky, representing the scattered remains of a dwarf galaxy that our Milky Way has been slowly consuming for over 1 billion years. Scientists from the European Space Agency's Gaia mission announced in 2018 that they had identified over 50 stellar streams in our galactic neighborhood, each representing a separate act of galactic cannibalism occurring at different stages of completion. Dr. Vasily Balakurov from Cambridge University, who led the discovery team, called it the most comprehensive evidence for ongoing galactic cannibalism ever assembled. Proof that our galaxy continues actively dismantling smaller systems rather than simply growing through peaceful accretion. Tonight, we're going to explore the most violent and ongoing process in our cosmic neighborhood. You're about to discover how the Milky Way's gravitational appetite has shaped our galaxy's structure, influenced the formation of our solar system, and continues determining the fate of every stellar system in our local group of galaxies. We will journey from the tidal streams that mark galactic crime scenes to the dark matter dynamics that power cosmic cannibalism across billions of years. But first, consider this chilling reality. The process that is transforming our galaxy through galactic cannibalism will eventually consume the Milky Way itself when our galaxy collides with the Andromeda Galaxy in approximately 4.5 billion years. The cosmic predator will become cosmic prey in the ultimate act of galactic cannibalism that will reshape our entire cosmic region. This isn't just about distant cosmic violence happening in galaxy clusters billions of light years away. This is about discovering that our own galactic home operates according to principles of cosmic predation that make galactic cannibalism as natural and inevitable as biological predation on Earth. What appears to be cosmic destruction reveals itself as cosmic evolution's method for building larger, more complex galactic ecosystems through systematic consumption of smaller cosmic communities. The ancient philosophers wondered whether cosmic order emerges from cosmic chaos or whether chaos destroys cosmic order. Modern astronomy has discovered something far more profound. Cosmic order emerges through cosmic chaos, with galactic cannibalism serving as cosmic evolution. That's primary mechanism for building galactic complexity through systematic destruction and reconstruction of cosmic structure. By the time we finish this cosmic investigation, you'll understand how galactic cannibalism has operated throughout cosmic history to build the massive galaxies we observe today, including our own Milky Way. You'll discover why every large galaxy bears the gravitational scars of consuming dozens or hundreds of smaller systems, making galactic cannibalism the dominant process in cosmic structure formation. You'll learn why the stellar streams surrounding our galaxy tell stories of cosmic violence spanning billions of years, revealing how galactic cannibalism operates through tidal forces that can stretch stellar systems across distances exceeding the size of entire galaxies. And I'll see why understanding galactic cannibalism reveals that cosmic evolution operates according to principles of systematic consumption that make destruction and creation inseparable aspects of cosmic development. The implications extend beyond astronomy to encompass fundamental questions about the nature of cosmic evolution, the inevitability of cosmic violence, and the relationship between destruction and creativity in building cosmic complexity. Galactic cannibalism represents cosmic evolution's method for concentrating matter and energy into increasingly massive and sophisticated cosmic structures through processes that span billions of years and billions of light years. Subscribe and hit the thumbs up button if you're ready to witness cosmic predation operating on scales that dwarf terrestrial imagination. And here is a question that will transform your cosmic perspective. If galactic cannibalism is natural and inevitable throughout cosmic evolution, what does that reveal about the relationship between destruction and creation in building cosmic complexity? Comment your most profound insights below. I'll pin the response that best captures the cosmic cannibalism occurring around us. The galaxy we call home isn't a peaceful cosmic island floating through empty space. It is an active cosmic predator that continues hunting and consuming neighboring stellar systems through gravitational forces so powerful they can tear apart cosmic structures that have existed for billions of years. We're about to discover that cosmic violence isn't separate from cosmic beauty. It is cosmic beauty's primary construction mechanism. The Milky Way that seems so stable and eternal from our terrestrial perspective reveals itself as a dynamic cosmic ecosystem built through systematic cannibalism that continues reshaping galactic structure through ongoing consumption of smaller galactic communities. Tonight, you're going to learn that you live within a cosmic predator whose appetite for galactic cannibalism will ultimately determine the structure and fate of our entire cosmic neighborhood. The universe that appeared to evolve through peaceful processes of cosmic expansion and structure formation actually evolves through systematic cosmic predation, where larger systems consume smaller systems in an endless cycle of galactic cannibalism that builds cosmic complexity through destruction and reconstruction operating across the vast scales of space and time that encompass everything we've ever known about cosmic evolution. Now, let us begin our journey into the heart of ongoing cosmic cannibalism that surrounds us everywhere we look into the night sky. Written in stellar streams that mark the scattered remains of galactic communities consumed by our cosmic predator home. Chapter 1. Galactic Predator. The Milky Way galaxy that serves as our cosmic home is far from the peaceful, stable stellar system that casual stargazers might imagine. Our galaxy operates as a cosmic predator of extraordinary efficiency, systematically hunting down and consuming smaller neighboring galaxies through gravitational forces so powerful they can tear stellar systems apart across distances spanning millions of light years. Understanding our galaxy's predatory nature requires grappling with gravitational dynamics operating on scales that dwarf human experience while revealing cosmic processes that have shaped galactic evolution for over 13 billion years. The predatory process begins with understanding that the Milky Way contains approximately 400 billion stars organized into a disk structure spanning 100,000 light-years in diameter, with a total mass exceeding 1 trillion solar masses when including dark matter components. This enormous gravitational mass creates tidal forces that extend far beyond our galaxy's visible boundaries, establishing a sphere of gravitational influence spanning several million light-years, where smaller galaxies become vulnerable to tidal disruption and eventual consumption. Dr. Katherine Johnston from Columbia University, who pioneered computer simulations of galactic cannibalism, explains that large galaxies like the Milky Way operate as gravitational vacuum cleaners that continuously sweep up smaller stellar systems through tidal stripping processes. When dwarf galaxies venture within approximately 300,000 light-years of our galactic center, they begin experiencing tidal forces that gradually stretch and distort their stellar distributions until their stars become gravitationally unbound from their original galactic homes. The Gaia Space Telescope has revolutionized our understanding of galactic cannibalism by providing precise measurements of stellar positions and velocities throughout the Milky Way's halo region. These observations reveal that our galaxy's outer regions contain numerous stellar streams, coherent groups of stars following similar orbital paths that represent the scattered remains of disrupted dwarf galaxies. Each stream tells the story of a separate act of galactic cannibalism, revealing our galaxy's predatory history written in stellar kinematics. The most spectacular example of ongoing galactic cannibalism involves the Sagittarius Dwarf Galaxy, a stellar system containing approximately 4 billion stars that our Milky Way has been consuming for over 1 billion years. The Sagittarius system represents the most massive stellar system currently being disrupted by our galaxy, creating the Sagittarius Stream, a river of stars that wraps around our entire galaxy multiple times and spans more than 360 degrees across Earth's sky. Computer simulations by Dr. James Bullock from the University of California, Irvine, demonstrate that the Sagittarius disruption process involves multiple paracentric passages, close approaches to our galactic center, that progressively strip stars from the dwarf galaxy's outer regions, while the remaining stellar core continues orbiting within our galactic halo. Each orbital passage removes additional stellar material, gradually reducing the Sagittarius system to a fraction of its original mass while distributing its stars throughout our galactic environment. But the Milky Way's predatory appetite extends far beyond consuming single dwarf galaxies to encompass systematic disruption of entire populations of smaller stellar systems. The Dark Energy Survey has identified over 40 previously unknown dwarf galaxies in our local group, many of which show evidence of tidal disturbance from interactions with our galaxy's gravitational field. These systems represent a feeding pipeline that continuously supplies fresh material for ongoing galactic cannibalism. The European Southern Observatory's very large telescope has conducted detailed spectroscopic studies of disrupted stellar systems, revealing that galactic cannibalism operates through multiple physical mechanisms depending on the mass ratio between predator and prey galaxies. Low-mass dwarf systems experience complete tidal disruption that scatters their stars throughout the galactic halo, while more massive systems can survive multiple encounters while losing substantial fractions of their stellar populations. The predatory process also involves dark matter dynamics that significantly complicate galactic cannibalism physics. Dwarf galaxies are embedded within dark matter halos that can be 10 times more massive than their stellar components, creating complex gravitational interactions during tidal encounters. Body simulations by Dr. Mario Matteo from the University of Michigan show that dark matter stripping often precedes stellar disruption, leaving stellar cores orbiting within dark matter-poor environments that accelerate subsequent tidal breakdown. The Atacama Large Millimeter Array has detected molecular gas streams associated with some disrupted stellar systems, revealing that galactic cannibalism affects not only stellar populations, but also interstellar medium components that provide raw materials for future star formation. The gravitational forces that disrupt stellar systems also heat and disperse galactic gas, potentially terminating star formation within consumed stellar systems while enriching our galaxy's gas reservoirs. NASA's Hubble Space Telescope observations of stellar populations within disrupted systems reveal that galactic cannibalism preferentially affects older stellar populations while leaving younger stars more concentrated within surviving galactic cores. This age-dependent disruption creates chemical gradients within stellar streams that preserve information about star formation, histories within consumed dwarf galaxies, enabling astronomical archaeologists to reconstruct the evolutionary histories of galactic meals. The predatory efficiency of galactic cannibalism becomes apparent when considering that computer simulations predict our galaxy should be surrounded by hundreds of dwarf galaxy satellites based on dark matter halo formation models, and observations reveal only a few dozen surviving systems. This missing satellites problem suggests that galactic cannibalism has been so thorough throughout cosmic history that most potential dwarf galaxy companions were consumed billions of years ago. Dr. Beth Willman from Haverford College has investigated the survival strategies that enable some dwarf galaxies to resist complete tidal disruption despite orbiting within our galaxy's gravitational sphere of influence. Surviving systems typically maintain highly elliptical orbits that minimize time spent within our galaxy's tidal radius, or possess unusually compact stellar distributions that resist gravitational stretching during close encounters. The predatory process also reveals remarkable precision in gravitational dynamics, since tidal forces must overcome the internal gravitational binding energy of dwarf galaxy stellar systems while preserving coherent stellar streams that remain detectable for hundreds of millions of years after disruption events. This requires gravitational interactions calibrated to specific force magnitudes that disrupt galactic structure without completely dispersing stellar populations. But perhaps the most profound aspect of galactic predation involves recognizing that our galaxy's cannibalistic behavior represents normal galactic evolution rather than exceptional cosmic violence. Every large galaxy in the observable universe exhibits evidence of consuming smaller stellar systems, making galactic cannibalism the primary mechanism for building galactic mass and complexity throughout cosmic history. Consider what this means for our understanding of cosmic evolution and galactic ecosystems. The Milky Way's predatory nature suggests that cosmic development operates according to principles where larger systems systematically consume smaller systems to achieve greater mass, complexity, and gravitational influence. This cosmic hierarchy extends from planetary accretion during solar system formation to galactic cannibalism during cosmic structure evolution. Your existence within a cosmic predator means that the calcium in your bones, the iron in your blood, and the oxygen you breathe were all processed through stellar nucleosynthesis within stellar systems that were subsequently consumed by galactic cannibalism and incorporated into our galaxy's chemical evolution. You are literally composed of the stellar remains of galactic communities that our cosmic home has systematically devoured across billions of years. Now we're going to explore the stellar streams that provide forensic evidence for ongoing galactic cannibalism, revealing how gravitational forces can stretch stellar systems across cosmic distances, while preserving detailed records of cosmic crimes that continue reshaping our galactic neighborhood. Chapter 2. Stellar Crime Scenes. The night sky above us is scattered with stellar crime scenes, vast streams of stars that mark the gravitational murder scenes where our galaxy has torn apart and consumed. Smaller stellar systems leaving behind cosmic evidence trails that stretch across millions of light years and preserve detailed forensic records of galactic cannibalism spanning billions of years. These stellar streams represent the most spectacular displays of cosmic violence visible to astronomical observation, revealing how gravitational forces can dismantle entire galactic communities while creating some of the most beautiful and scientifically valuable structures in our cosmic neighborhood. The forensic investigation begins with understanding that stellar streams form through tidal disruption processes that operate like cosmic torture devices, gradually stretching stellar systems beyond their gravitational breaking points while preserving the orbital characteristics of disrupted stars in coherent kinematic patterns. When a dwarf galaxy approaches our galactic center, differential gravitational forces tidal forces begin pulling more strongly on the galaxy's near side than its far side, creating internal stress that gradually overcomes the dwarf galaxy's gravitational self-binding. Dr. Wynne Evans from Cambridge University, who has spent decades studying stellar streams, describes them as cosmic DNA evidence that preserves detailed information about both the consumed stellar system and the gravitational dynamics responsible for its destruction. Each stellar stream encodes the mass, orbital history, star formation timeline, and chemical evolution of its parent dwarf galaxy, while also revealing the gravitational structure of our Milky Way through the precise way tidal forces shape the disruption process. The most famous stellar crime scene spans the entire sky in the form of the Sagittarius stream, discovered in 2003 through systematic analysis of stellar positions and velocities measured by the 2-micron all-sky survey. This stream represents the ongoing disruption of the Sagittarius Dwarf Elliptical Galaxy, creating a stellar river that wraps around our galaxy at least twice and contains stars distributed across more than 360 degrees of sky, making it the largest single structure visible from Earth. The Gaia space mission has transformed stellar stream forensics by providing unprecedented precision in measuring stellar positions, velocities, and chemical compositions for billions of individual stars throughout our galactic neighborhood. These measurements reveal that the Sagittarius stream actually consists of multiple strand structures created during different orbital passages, with each strand preserving information about the gravitational environment during specific disruption epochs spanning the past billion years. Computer simulations by Dr. Rodrigo Ibera from the University of Strasbourg demonstrate that creating the observed Sagittarius stream structure requires the Sagittarius Dwarf Galaxy to have made at least 3 close approaches to our galactic center, with each passage stripping additional stellar material while the remnant core continues its highly elliptical orbit. The stream's complex morphology reveals our galaxy's dark matter distribution by showing how gravitational forces shape stellar trajectories during disruption events. But the Sagittarius stream represents only the most prominent example among dozens of stellar streams that surround our galaxy like a cosmic web of galactic carnage. The European Space Agency's Gaia mission has identified over 60 distinct stellar streams in our galactic halo, each representing a separate dwarf galaxy that our Milky Way has consumed through tidal disruption processes operating across different timescales and orbital configurations. The Helmi stream, discovered by Dr. Amina Helmi from the University of Groningen, preserves evidence of a galactic merger that occurred approximately 8 billion years ago when our galaxy was much smaller and less massive than today. This ancient stellar stream demonstrates that galactic cannibalism has operated throughout our galaxy's entire evolutionary history, systematically consuming smaller stellar systems to build the massive galactic structure we observe today. More recently discovered streams, like the GD1 stream, reveal ongoing disruption of globular star clusters, dense stellar associations that orbit within our galaxy's gravitational field. The GD1 stream shows evidence for gravitational perturbations caused by dark matter subhalos, providing direct observational tests of dark matter distribution and composition within our galactic environment through the way dark matter clumps affect stellar stream morphology. The forensic analysis extends to chemical archaeology, since different stellar streams preserve distinct chemical signatures reflecting the star formation histories and chemical evolution patterns of their parent dwarf galaxies. Dr. Anna Frebel from MIT has conducted detailed spectroscopic studies of stream stars, revealing that consumed dwarf galaxies had different chemical enrichment patterns than stellar populations that formed within our galaxy, enabling astronomers to distinguish between accreted and in situ stellar populations. NASA's Hubble Space Telescope has identified stellar streams in external galaxies, revealing that galactic cannibalism operates universally throughout cosmic structure rather than representing unusual behavior specific to our local group environment. The Andromeda Galaxy, our nearest large galactic neighbor, exhibits an even more complex system of stellar streams, indicating more extensive galactic cannibalism than our own galaxy has experienced. The crime scene analysis also reveals temporal aspects of galactic cannibalism through stellar age dating techniques that determine when disruption events occurred and how long stellar streams remain coherent before dispersing into the galactic halo background. Stellar streams typically remain detectable for 1 to 2 billion years after disruption events, providing observational windows into galactic cannibalism processes spanning significant fractions of cosmic time. Dr. Vasily Belokharov's systematic surveys using machine learning algorithms have automated stellar stream detection in Gaia datasets, revealing previously unknown streams and demonstrating that our galactic halo contains far more substructure than previously recognized. These surveys suggest that galactic cannibalism has been more extensive and more recent than earlier observations indicated, with new streams being discovered regularly as data analysis techniques become more sophisticated. The European Southern Observatory S4MOST survey will soon provide detailed chemical and kinematic measurements for millions of halo stars, enabling comprehensive reconstruction of our galaxy's accretion history through systematic analysis of stellar stream populations. These observations will reveal how galactic cannibalism has operated throughout cosmic history while testing theoretical models of cosmic structure formation through direct observation of disruption products. But stellar streams also reveal surprising aspects of galactic dynamics that weren't apparent from studying intact stellar systems. The coherent structure of stellar streams demonstrates that our galaxy's gravitational field remains remarkably smooth and stable across timescales of hundreds of millions of years, since gravitational irregularities would disrupt stream coherence and create kinematic scatter that would erase forensic evidence. The preservation of stellar streams also indicates that galactic cannibalism operates through gentle tidal processes rather than violent collisional disruption, allowing stellar systems to be gradually dismantled while preserving orbital information and chemical characteristics that enable detailed forensic reconstruction of galactic merger histories. This gentle violence creates beautiful cosmic structures while systematically destroying galactic communities. Consider the remarkable fact that you can observe stellar crime scenes directly by looking up at the night sky, since several stellar streams are visible to careful naked eye observation under dark skies. The constellation Sagittarius marks the direction toward the core remnant of our galaxy's most recent major meal, while the stellar stream itself extends across the entire celestial sphere as evidence of ongoing cosmic cannibalism. Your existence within a galaxy surrounded by stellar crime scenes means that cosmic violence operates continuously in your immediate cosmic neighborhood while remaining invisible to casual observation. The peaceful night sky conceals evidence of systematic galactic predation that has shaped every aspect of our galactic environment across billions of years of cosmic evolution. The stellar streams that mark galactic crime scenes also reveal that cosmic beauty and cosmic violence are inseparable aspects of cosmic evolution, since the same gravitational processes that create spectacular stellar rivers also destroy galactic communities that may have contained billions of stars, planetary systems, and potentially entire civilizations whose remains now decorate our cosmic neighborhood. Now we're going to explore the tidal forces that power galactic cannibalism, revealing how gravitational dynamics can stretch stellar systems across cosmic distances while demonstrating the incredible precision required for cosmic violence to create cosmic beauty through systematic destruction and reconstruction of galactic structure. Chapter 3. Tidal Forces. The cosmic violence that enables galactic cannibalism operates through tidal forces, gravitational effects so subtle they are barely noticeable within our solar system, yet so powerful across galactic distances. They can tear apart stellar systems containing billions of stars while stretching cosmic structures across millions of light years with precision that rivals the most sophisticated engineering projects ever conceived. Understanding tidal forces reveals how the universe accomplishes cosmic construction through cosmic destruction, using gravitational dynamics to build galactic complexity through systematic dismantling of smaller cosmic communities. Tidal forces emerge from the fundamental principle that gravitational attraction depends on distance, creating force gradients across extended objects that experience different gravitational accelerations at different locations within gravitational fields. When a dwarf galaxy approaches our Milky Way stars on the galaxy's near side, experience stronger gravitational attraction toward our galactic center than stars on the far side, creating internal stress that gradually overcomes the dwarf galaxy's gravitational self-binding and pulls the stellar system apart. Dr. Simon White from the Max Planck Institute for Astrophysics explains that tidal disruption operates like cosmic taffy pulling, where gravitational gradients stretch stellar systems beyond their elastic limits while preserving the kinematic relationships between disrupted stars. The mathematical description of tidal forces involves second derivatives of gravitational potential, making tidal effects proportional to the mass of the disrupting galaxy divided by the cube of separation distance. This inverse cube dependence means that tidal forces become dramatically stronger as dwarf galaxies approach our galactic center, creating a critical radius, the Roche limit, where tidal forces exceed internal gravitational binding. For dwarf galaxies orbiting the Milky Way, this critical radius typically occurs at distances of 50,000 to 100,000 light-years from our galactic center, depending on the dwarf galaxy's mass distribution and orbital velocity. The European Space Agency's Gaia mission has measured tidal forces in action by tracking individual stars within disrupting dwarf galaxies as they experience gravitational stretching across multiple orbital periods. These observations reveal that tidal disruption doesn't occur instantaneously, but proceeds gradually over hundreds of millions of years, with each orbital passage removing additional stellar material while the remaining galactic core continues its highly elliptical trajectory. Computer simulations by Dr. Katherine Johnston demonstrate that tidal forces create characteristic velocity patterns within disrupting stellar systems, generating leading and trailing tidal tails that stretch in opposite directions along orbital paths. The leading tail contains stars that were accelerated ahead of the dwarf galaxy's motion, while the trailing tail contains stars that were decelerated and fall behind the galactic core, creating symmetrical stellar streams that preserve orbital information across cosmic time. The precision of tidal disruption becomes apparent when examining how gravitational forces must be calibrated to create coherent stellar streams rather than completely dispersing stellar systems into random distributions. Too weak and dwarf galaxies would survive intact indefinitely. Too strong and stellar systems would be completely shredded without leaving coherent kinematic structures that remain detectable across hundreds of millions of years. NASA's Hubble Space Telescope has observed tidal disruption in real time around external galaxies, revealing how tidal forces operate across different cosmic environments and galactic mass scales. The antennae galaxies provide spectacular examples of tidal tail formation during major galactic mergers, where gravitational interactions between comparable mass systems create extended stellar streams spanning hundreds of thousands of light-years. But tidal forces in galactic cannibalism operate differently from tidal interactions between comparable mass systems, since the extreme mass ratio between large galaxies like the Milky Way and dwarf galaxy satellites creates asymmetric disruption processes. The massive galaxy remains essentially unperturbed, while the dwarf galaxy experiences complete structural transformation, making galactic cannibalism a fundamentally one-sided gravitational interaction. The Atacama Large Millimeter Array has detected tidal effects on interstellar gas within disrupting dwarf galaxies, revealing that gravitational forces affect both stellar and gaseous components of galactic systems. Gas typically experiences stronger tidal effects than stars due to its lower density and weaker gravitational binding, often being stripped completely, while stellar cores survive multiple orbital passages. Dr. Marla Jiha from Yale University has studied tidal effects on star formation within disrupting dwarf galaxies, finding that gravitational stress typically terminates star formation activity long before complete stellar disruption occurs. This process, called tidal quenching, explains why many dwarf galaxies in our local group contain only ancient stellar populations, despite having sufficient gas reservoirs to sustain continued star formation. The mathematical framework for tidal forces involves complex orbital mechanics that must account for the three-dimensional gravitational field structure of our galaxy, including contributions from dark matter halos, stellar disk components, and central bulge regions. Each component contributes different tidal force characteristics that affect disruption dynamics, depending on orbital inclination, eccentricity, and pericentric distance. Advanced on-body simulations require millions of computational particles to accurately model tidal disruption processes while accounting for gravitational interactions between individual stellar system components and time-varying gravitational fields caused by our galaxy's rotation and structural evolution. These simulations reveal that tidal disruption creates fractal-like substructure within stellar streams, with smaller streams branching off larger ones in hierarchical patterns. The European Southern Observatory (SMU) spectrograph has measured velocity dispersions within tidal streams to test whether disrupted stellar populations maintain thermal equilibrium during stretching processes. These observations reveal that tidal heating, energy injection from gravitational stretching, can increase stellar velocities within disrupted systems while preserving overall kinematic coherence across stream structures. But tidal forces also reveal fundamental aspects of dark matter distribution within our galaxy, since the detailed morphology of stellar streams depends sensitively on the gravitational field strength and geometry throughout our galactic halo. Deviations from smooth tidal stream morphologies indicate gravitational perturbations caused by dark matter subhalos, providing direct observational tests of dark matter clumping predicted by cosmic structure formation models. The Vera Rubin Observatory will soon begin detecting stellar streams around hundreds of nearby galaxies, enabling comparative studies of tidal disruption processes across different galactic environments and mass scales. These surveys will reveal whether galactic cannibalism operates according to universal principles or varies significantly, depending on cosmic context and galactic evolutionary history. Consider the remarkable precision required for tidal forces to create the beautiful stellar stream structures we observe throughout our galactic neighborhood. The same gravitational dynamics that operate according to simple inverse square laws produce cosmic architecture of extraordinary complexity and beauty while systematically dismantling stellar communities through processes that span hundreds of millions of years. Tidal forces demonstrate how cosmic destruction and cosmic creation represent inseparable aspects of cosmic evolution, with gravitational dynamics that dismantle dwarf galaxies simultaneously building the extended halo structure that comprises most of our galaxy spatial volume. The stars scattered by tidal disruption don't disappear. They become incorporated into our galaxy's architectural framework. Your existence within a galaxy shaped by tidal forces means that the cosmic environment surrounding our solar system has been sculpted by gravitational violence operating across scales that dwarf terrestrial experience. Every aspect of our galactic structure reflects billions of years of tidal disruption processes that continue reshaping cosmic architecture through ongoing galactic cannibalism. The tidal forces that enable galactic cannibalism operate with such precision and beauty that they transform cosmic violence into cosmic art, creating stellar streams that span our entire sky while preserving detailed records of gravitational interactions spanning billions of years of cosmic evolution. These forces reveal that cosmic evolution operates according to principles where destruction becomes construction and violence becomes beauty. Now we're going to explore dark matter's crucial role in galactic cannibalism, revealing how invisible cosmic components influence the dynamics of galactic consumption and why understanding dark matter is essential for comprehending the full scope of cosmic predation operating throughout our cosmic neighborhood. Chapter 4. Dark Matter Dynamics. The cosmic cannibalism consuming our galactic neighborhood operates through dark matter dynamics that remain largely invisible to direct observation, yet control every aspect of galactic disruption, merger timescales, and structural evolution across cosmic time. Dark matter comprises approximately 85% of all gravitational mass in galactic systems, creating the underlying architecture upon which stellar components organize themselves, while determining how galactic cannibalism proceeds through gravitational interactions that extend far beyond visible galactic boundaries into vast dark matter halos spanning millions of light years. Understanding dark matter's role in galactic cannibalism begins with recognizing that both predator and prey galaxies are embedded within dark matter halos that can be 10 times more massive than their visible stellar components. The Milky Way's dark matter halo extends at least 1 million light-years from our galactic center, creating a gravitational sphere of influence that captures and disrupts smaller stellar systems long before they approach our galaxy's visible disk structure. Dr. Carlos Frank from Durham University, whose computer simulations have revolutionized our understanding of dark matter dynamics, explains that galactic cannibalism fundamentally represents dark matter halo interactions rather than stellar system mergers. When dwarf galaxies enter our galaxy's dark matter halo, they begin experiencing gravitational forces that preferentially strip their own dark matter components, while stellar cores can survive multiple orbital passages within increasingly dark matter-poor environments. The Lambda-CDM model of cosmic structure formation predicts that dark matter halos form through hierarchical assembly processes where smaller halos merge to build progressively larger structures across cosmic time. Computer simulations like the Millennium 2 project reveal that massive dark matter halos like our galaxy should contain hundreds of smaller dark matter subhalos representing the remnants of consumed dwarf galaxy systems. Most of these subhalos have lost their stellar components through tidal stripping, existing as dark satellites that remain gravitationally bound within our galactic environment despite being completely invisible to optical telescopes. The Via Lactea simulation, conducted by Dr. Michael Cohen from the University of California, Berkeley, demonstrates that dark matter subhalo populations exhibit specific spatial and velocity distributions that reflect the orbital dynamics of galactic cannibalism across cosmic time. These simulations predict observable consequences for stellar stream morphologies, satellite galaxy survival rates, and gravitational lensing effects that can test dark matter models through astronomical observations. But dark matter dynamics create profound complications for understanding galactic cannibalism. Since dark matter interactions operate through gravitational forces alone while remaining immune to hydrodynamic effects, stellar feedback, and electromagnetic processes that significantly affect ordinary matter components. This differential behavior means that dark matter and stellar components of dwarf galaxies can evolve along different trajectories during tidal encounters. The European Space Agency Gaia mission has detected kinematic signatures of dark matter subhalos through their gravitational perturbations of stellar streams, providing the first direct observational evidence for dark matter structure within our galactic halo. These perturbations appear as gaps, or spurs in otherwise smooth stellar streams, created when dark matter clumps gravitationally deflect stream stars during close encounters. Dr. Aina Bonaka from the Center for Astrophysics has identified specific perturbations in the GD1 stellar stream that indicate interactions with dark matter subhalos containing way solar masses, exactly the mass range predicted for stripped dwarf galaxy remnants by dark matter simulation models. These observations provide crucial tests of dark matter's particle nature and distribution within galactic environments. The Sloan Digital Sky Survey has revealed that our galaxy contains fewer visible satellite galaxies than dark matter simulations predict, creating the missing satellites problem that suggests either dark matter models are incomplete or galactic cannibalism has been more efficient at destroying dwarf galaxy stellar populations than theoretical predictions indicate. Alternative explanations propose that dark matter exhibits self-interaction properties that weren't included in early simulation models, potentially affecting subhalo survival rates and spatial distributions within massive galactic halos. Self-interacting dark matter could explain discrepancies between observed and simulated satellite populations while maintaining consistency with cosmic structure formation on larger scales. The Dark Energy Survey has discovered ultra-faint dwarf galaxies that appear to be dark matter-dominated systems with mass-to-light ratios exceeding 1,000 to 1, representing the most dark matter-rich stellar systems ever observed. These systems might represent the final stages of galactic cannibalism, where stellar populations have been reduced to minimal levels, while substantial dark matter halos remain gravitationally bound. NASA's Remnants Space Telescope will conduct comprehensive weak gravitational lensing surveys that can directly measure dark matter distributions around our galaxy and throughout the local group, providing independent tests of dark matter substructure predicted by galactic cannibalism models. These observations will reveal whether dark matter halos exhibit the complex internal structure expected from hierarchical assembly through cosmic time. But dark matter dynamics also influence the long-term fate of galactic cannibalism within our local group, since dark matter interactions between our galaxy and the Andromeda Galaxy will determine merger timescales and structural outcomes. When these massive systems collide in approximately 4.5 billion years, dark matter friction effects could accelerate merger processes, while dark matter redistribution will determine the final equilibrium configuration. Advanced unbody simulations by Dr. T.J. Cox from Harvard University predict that the Milky Way Andromeda merger will create a massive elliptical galaxy, dubbed Milkomeda, with a dark matter halo containing the combined mass of both progenitor systems, plus additional dark matter captured from the local group environment during gravitational encounters, spanning several billion years. The Illustra Simulation Project has modeled dark matter's role in galactic cannibalism across cosmic time, revealing that dark matter dynamics naturally explain the observed diversity of galactic morphologies and mass distributions throughout the observable universe. Spiral galaxies, elliptical galaxies, and dwarf systems all represent different outcomes of dark matter-driven cannibalism processes, operating under varying environmental conditions. Consider the profound implications of dark matter controlling galactic cannibalism throughout cosmic structure. The invisible cosmic majority that comprises 85% of gravitational mass operates according to principles we barely understand while determining the fate of every visible stellar system through gravitational dynamics that span billions of years and millions of light years. Your existence within a galaxy whose structure and evolution are controlled by dark matter means that cosmic reality operates primarily through invisible components whose nature remains fundamentally mysterious despite determining every aspect of cosmic architecture. The galactic cannibalism reshaping our cosmic neighborhood proceeds according to dark matter dynamics that exceed our direct observational capabilities. Dark matter's role in galactic cannibalism also reveals that cosmic evolution operates through hidden processes that control visible cosmic structure while remaining essentially incomprehensible to direct investigation. Understanding galactic cannibalism requires grappling with cosmic components that remain invisible yet dominate cosmic dynamics across every scale of cosmic organization. The dark matter dynamics powering galactic cannibalism demonstrate that most of cosmic reality remains hidden from direct observation while controlling every visible aspect of cosmic structure formation. Galactic cannibalism represents just the visible manifestation of dark matter interactions operating throughout cosmic space, according to principles that continue challenging our understanding of cosmic reality. Now we're going to explore the merger timeline that governs galactic cannibalism, revealing how cosmic consumption proceeds across timescales spanning billions of years while following predictable patterns that determine the ultimate fate of every stellar system in our cosmic neighborhood. Chapter 5. Merger Timeline. Galactic cannibalism operates according to cosmic timelines that span billions of years, following predictable sequences of gravitational encounters, orbital decay, and structural transformation that determine how cosmic predation proceeds from initial capture through final consumption. Understanding these merger timelines reveals how gravitational dynamics can sustain cosmic violence across timescales that exceed the entire history of complex life on Earth, while demonstrating the extraordinary patience required for cosmic evolution to build galactic complexity through systematic consumption of smaller stellar systems. The merger timeline begins with gravitational capture, when smaller stellar systems first enter the extended dark matter halo surrounding massive galaxies like our Milky Way. This initial capture typically occurs at distances of 1 to 2 million light-years from galactic centers, where tidal forces remain too weak to cause immediate disruption, but strong enough to alter orbital trajectories and begin the long process of orbital decay through dynamical friction mechanisms. Dynamical friction represents a gravitational drag effect discovered by Subramanian Chandrasekhar in the 1940s, where massive objects moving through gravitational fields experience deceleration caused by gravitational wake effects in surrounding dark matter distributions. As dwarf galaxies orbit within our galactic halo, they gravitationally attract dark matter particles, creating overdense regions that exert backward gravitational forces and gradually reduce orbital energy. Dr. Piero Madà from the University of California, Santa Cruz has calculated that dynamical friction timescales depend on orbital parameters, satellite galaxy mass, and dark matter halo properties according to complex mathematical relationships that determine merger rates throughout cosmic structure. For typical dwarf galaxies orbiting the Milky Way, dynamical friction requires 5 billion years to reduce orbital separations to distances where tidal disruption becomes significant. The orbital decay process creates characteristic evolutionary sequences where captured satellite galaxies transition from wide, highly elliptical orbits through progressively smaller, more circular trajectories that bring them closer to our galactic center with each orbital passage. The European Space Agency's Gaia mission has tracked this orbital evolution for several dwarf galaxies, confirming theoretical predictions about merger timeline progression. Tidal disruption typically begins when dwarf galaxies reach paracentric distances of 50,000 to 100,000 light-years from our galactic center, depending on satellite galaxy mass and internal structure. Initial disruption episodes remove stars from outer galactic regions while leaving central stellar cores intact, creating the first stellar streams that mark the beginning of active galactic cannibalism. Computer simulations by Dr. Mario Matteo from the University of Michigan demonstrate that tidal disruption proceeds through multiple phases characterized by different mass loss rates and structural evolution patterns. Early disruption phases remove 10 to 20% of satellite galaxy mass per orbital passage, while later phases can remove 50% or more as tidal forces penetrate deeper into disrupted stellar systems. The Sagittarius Dwarf Elliptical Galaxy provides the most detailed observational record of merger timeline evolution. Since this system has been undergoing active disruption for over 1 billion years while remaining sufficiently massive to preserve its central stellar core. Observations revealed that the Sagittarius system has lost approximately 80% of its original stellar mass, while creating stellar streams that wrap around our entire galaxy multiple times. But merger timelines vary dramatically depending on orbital characteristics, satellite galaxy properties, and environmental factors that influence gravitational dynamics throughout cosmic evolution. Dr. Andrew Wetzel from UC Davis has studied merger timeline diversity using the FIRE cosmological simulations, revealing that some dwarf galaxies survive for over 10 billion years within massive galactic halos, while others are completely disrupted within 1 to 2 billion years of initial capture. The merger timeline also depends on whether satellite galaxies contain dark matter halos that provide additional gravitational binding energy, since dark matter-rich systems resist tidal disruption more effectively than stellar systems with reduced dark matter content. Recent discoveries of dark matter-free dwarf galaxies suggest that some systems might have already lost their dark matter components through earlier gravitational encounters, accelerating subsequent stellar disruption processes. NASA's Hubble Space Telescope has observed merger timelines in external galaxies, revealing that galactic cannibalism operates according to similar temporal patterns throughout cosmic structure, despite variations in galactic masses, environmental densities, and cosmic epochs. The Andromeda Galaxy exhibits stellar stream systems indicating ongoing consumption, processes spanning several billion years of galactic evolution. The merger timeline perspective reveals that galactic cannibalism represents a continuous background process rather than discrete merger events, with our galaxy simultaneously consuming dozens of smaller stellar systems at different stages of orbital decay and tidal disruption. This ongoing consumption creates a steady supply of accreted stellar material that contributes approximately 1 to 2% of our galaxy's stellar mass per billion years. Advanced unbody simulations predict that merger timelines will dramatically accelerate when our Milky Way begins interacting gravitationally with the Andromeda Galaxy, approximately 2 to 3 billion years from now. The approach phase will trigger enhanced tidal interactions throughout the local group environment, potentially disrupting satellite galaxies that have survived billions of years of gradual orbital decay through individual galactic encounters. The illustrious simulation project has modeled merger timelines across cosmic time, revealing that galactic cannibalism operated more rapidly during earlier cosmic epochs when cosmic structure was denser and gravitational encounter rates were higher. Early galactic assembly involved merger timelines of hundreds of millions rather than billions of years, reflecting the higher energy environments characterizing cosmic structure formation during the universe's youth. Dr. Sharda Jaggi from the University of Texas has investigated how merger timelines affect galactic chemical evolution, since accreted stellar populations bring different chemical compositions that reflect star formation histories within consumed dwarf galaxies. These chemical signatures remain detectable for billions of years after merger completion, enabling astronomical archaeologists to reconstruct galactic cannibalism timelines through stellar spectroscopy. The James Webb Space Telescope will observe merger timelines during cosmic dawn epochs, revealing how galactic cannibalism proceeded when the universe was younger and galactic masses were smaller. These observations will test whether merger timelines have evolved systematically throughout cosmic history or maintain similar characteristics across different cosmic environments and evolutionary stages. But merger timelines also reveal philosophical implications about the relationship between cosmic time and cosmic violence. Since galactic cannibalism demonstrates that cosmic destruction can proceed so gradually that it appears peaceful from any individual perspective, while systematically dismantling stellar communities across timescales that dwarf biological, evolution, or technological development. Consider that the merger timeline consuming the Sagittarius Dwarf Elliptical Galaxy has proceeded for longer than complex life has existed on Earth, yet represents only a single feeding event within our galaxy's ongoing cannibalistic appetite. The cosmic patience required for galactic predation exceeds human temporal experience by factors of thousands while operating according to gravitational inevitability that makes cosmic consumption as natural as planetary orbits. Your existence occurs during a brief moment within merged timelines that span billions of years. Yet cosmic cannibalism continues, reshaping your galactic environment according to gravitational dynamics established long before Earth formed and destined to continue long after our solar system ceases to exist. You live within cosmic violence, so gradual it appears as cosmic stability from terrestrial perspective. The merger timelines governing galactic cannibalism reveal that cosmic evolution operates according to temporal scales that make individual lifetimes, species evolution, and technological civilizations appear as instantaneous events within cosmic processes that reshape galactic architecture across billions of years of patient gravitational consumption. Now we're going to explore how galactic cannibalism has shaped the formation and evolution of our solar system, revealing the surprising ways that cosmic violence influences planetary development and the conditions that enable life to emerge and evolve within cosmic environments shaped by systematic stellar consumption.